So in this video, we are going to start a new topic called filter structures. So what are filter structures? Basically, you have got transfer functions or the LCCD representations. Now you want to implement them into a useful real filter in the sense that with the help of basic units like a delay or an adder or a multiplier. So all these components you want to use to assemble a real filter structure, a real filter on breadboard or something like that on a DSP kit, right? So okay, so filter structures. So many different implementations are possible for same filter. Like same filter can be represented and implemented in various ways. And all these implementations, they differ in the cost, because if you have more components and more costly components, then cost will go up. Speeds, uh, so uh, depending on different implementations, the speeds may vary, the layout, the noise performance, etc. Okay, so let's start with uh, the basics, block diagrams. So what are block diagrams? They are useful way to illustrate implementations. So okay, so you have some HZ, and given an HZ, how do you find out the block diagram representation? So let's say my HZ is given. I will take the same example here. G1Z upon 1 minus G1, G2. Sum G1Z upon 1 minus G1Z, G2Z. In case you are wondering what are these G1Z, G2Z, look at this figure. This could be your, so basically the components, I think in some previous lecture, we also discussed the basic components are addition, maybe I'll write down here. The basic components are an adder, a multiplier, right? We have discussed this before, just a recap, and uh, uh, and a delay function, a time delay. And these are basic components. So these G1Z and G2Z are consisting of these basic components, and we arrange them to formulate an HZ. Okay, so basically, how do we do that? So you write it down in terms of YZ upon HZ. So this is YZ upon XZ. And now you know YZ times, uh, so YZ minus YZ G1Z G2Z is equal to G1Z XZ. Okay, so you get YZ is G1Z times XZ plus G1Z G2Z times YZ. So basically this is your YZ, the output, and this is your input X of Z, and you're multiplying XZ with some GZ. I can take, this was G1Z. I can take this G1Z outside as common, and I can erase this one, right? So what does this show me? So in this one, so basically I have XZ plus G2Z coming here and getting added, right? And the output, so this basically this output is xz plus g2z. This gets multiplied with g1z. So in this way, um, I can represent this given hz in terms of a block diagram. Okay, now the other way. Uh, oh, I think I did the other way. So, uh, given a given HZ, given HC, how do we make block diagram? So that is the thing which we just now discussed. Now, given the block diagram, how do we make, how do we find HC? I can write it down here. So we are now given a block diagram. How do we find H of C? Okay, my block diagram is something like this. Let me check. G1Z. Here I have a G2Z. Now the question is, this is my X of Z, this is my Y of Z. How do I find out my H of Z? So very simple. So the trick is that I think I will, it's written here, output of summers as dummy variables. So whenever the output of the summer is considered a dummy variable and everything else is just multiplicative. Okay. So this dummy variable, so what is the value here? Let me call it as W of Z. So what is my W of Z? W of Z is basically equal to XZ plus G2 times Y of Z, right? And what is my YZ now? My Y of Z is G1 times W of Z, that is it. So I can substitute the value of W from above. So this becomes G1Z times XZ plus G2Z YZ. That is it. So this is my YZ. Now I can simplify. So my YZ uh, is equal to G1Z XZ, and this term G1 G2 Y can go here and it can come down like this, 1 minus G1 G2. Right. So in this way, and now I know my YZ upon XZ is my H of Z, so this term goes away. This is my H of Z. Okay, so that's it. So now more complicated block diagram. So this is an example. So given this block diagram, how do I find my H of Z? Okay, it's very simple. So you give some dummy names to the outputs of the summers, like W1. What is W1? This is XZ or XN. Okay, XZ minus alpha times Z inverse W3. So W1Z, basically you call it as W1, omit Z for the time being, just for simplicity, simple representation. X minus alpha Z inverse W3, right? Okay, now what is W2? W2 is W1 and through this path minus delta Z inverse W2, right? And what is W3? W3 is basically uh, this is okay W2 times epsilon plus Z inverse times W2. Okay, W2 times epsilon plus Z inverse times W2, right? That is W3. Now, what is my Y? Y is, okay, this is the path, W1 times beta plus W3 Z inverse times gamma. Okay, okay, it's here. So W1 times beta plus W3 Z inverse times gamma. That is Y. Now I have to write y only in terms of x. So basically I have to solve these equations to omit w1, w2 and w3. I have got four equations and three unknowns, and I can omit three variables. So finally I substitute the value of w3 and w1 from these equations, and I get uh, y in terms of x. So okay, so basically y upon x comes out to be this term, and this term is a division. The numerator is a second degree polynomial. Denominator is also a second degree polynomial. Okay, so means two poles and two zeros. Okay, now there is one point of caution: delay free loops are not possible. So there is, see, this is the loop. So these are not possible to implement. So see, this is a loop, and so my u is simply x plus y, right? And my v is another input. There are two inputs, x and v are the inputs, and this output of this summer is what? It is au plus v, and y is b times this. So b times au plus v, and u is x plus y. So this is what I get. Y is equal to b times v plus a x plus y. Okay. Now there is a problem here that at the same time, to calculate yn, I need yn. This is not possible, right? Because I don't know yn. How can I use it in the formulation here? So this is practically not possible, not implementable, right? So, but there is a possibility with the same equation I can find an implementable implementation. How do I do that? I simplify this. So basically I take this y to the other side, and I can say, I will write here, yn is equal to b times vn plus ba times xn, right? Ba times xn plus ba times yn, which I take to the other side and then divide. So this is 1 minus ba, right? That is it. So this is what is also derived here, bv plus bax upon 1 minus ba. So this is the thing which we have obtained. Okay, so and I can implement this implementation, right? This is possible. So there is this figure, there is no loop here, and it is implementable. Okay, now let's go on to the next thing. So okay, so as we discussed that different filters have one filter can have different implementations, and different implementations will have different costs of implementation, right? So let's try to focus on minimizing the number of components needed to make a structure, to make an implementation. So we are minimizing the number of components needed. And how do we do that? So okay, so there are some tricks which are possible. So basically we are trying to find what structures are equivalent, and then we can compare amongst these equivalent structures. This one uses the minimum number of components, right? So let's see how to find equivalent structures. So one way of finding equivalent structures is commutation, that AB is equal to BA. So we can flip their positions, or we can exchange their positions if they are occurring serially. Another factor which can be used is another way of finding equivalent structures is factoring. So we can factor, let's say if we have AB plus CB, then I can take B common, it becomes A plus C times B. Now you see in this structure, if you consider separate blocks, if A is a block, B is a block, and then you are adding it here, and here C is a block, B is a block. So basically something like this you are getting. So how many blocks you have? 4 blocks. But here, if I take B to the other side, if I take B common here, then I need only 3 blocks. So this means there is less computations involved. Uh, um, um, but here, if I merge these two structures, then fewer blocks are involved. So in this way, we can kind of optimize what we want. If I want less computations, or do I want lesser number of blocks? Because lesser number of blocks means faster implementation. I can implement it very fast because the minor delays will be minimized. Because I can group this into an efficient IC. Okay. Um, then we have another way to find equivalent structures, that is transpose. This is a very useful thing. Okay, so what we do is, first of all, we reverse the paths. So basically, here we had, let me take this pen. We had the path was left to right. Basically, all the arrows were here. So I reverse the paths means I put the arrows here. So I will, let me draw it here again. Oh, I'm sorry. So I have B1. So first of all, I reverse the paths. Okay, like this, like this, like this, like this, like this. So which means this becomes my output, this becomes my input, right? And secondly, what I do is I make adders into nodes and nodes into adders. So wherever there is a splitter node, so this node, I make it into an adder. This node, I make it into an adder. So wherever the input was getting split, now here it is getting joined. So this is an adder here, this is an adder here. And wherever the adders were there, I make them into nodes, right? So this one becomes a node. So as you see here, and then inputs become outputs. So input to this component becomes the output. So basically the direction is reversed. So B1, instead of pointing left to right, now it points right to left. So this is efficient implement. This is an equivalent implementation. It's called the transpose implementation. Okay, so basically you can derive this transpose implementation by some simple mathematical manipulation using the principles which we learned before. These principles, commutation and factoring. These two are very powerful principles. So you see B1x plus B2 Z inverse. So I'm just taking out Z inverse as common here, and rest everything is same. So this implementation is this. So you can see the equivalence. Okay, now let's move on. Okay, so the goal is to minimize the number of components that are required, and try to take as many common factors as possible. So why to have, so take as many factors common as possible to minimize computations. Minimize computations in the implementation. Okay. Uh, that's it. So I think this was the basics for implementation. And now in the next video, we'll see FIR filter structures. Thank you very much.